I said at the beginning of the semester that a lot of the material in this class is common sense, just formalized mathematically. This section definitely falls into that category. It is the pigeonhole principle. The pigeonhole principle states that if n pigeons fly into m pigeonholes and n is greater than m, then at least one hole must contain 2 or more pigeons. This is illustrated in the figure here. Like I said, common sense. If there's more occupants than there are holes, then one of the holes is, at least one of the holes is going to have more than one occupant. But has to be stated formally to be used in mathematical arguments and all that sort of stuff. Pigeonhole principle stated formally is a function from one finite set to a formal or to a smaller finite set cannot be one-to-one. There must be at least 2 elements in the domain that have the same image in the codomain. Like I said, this is pretty much common sense, but it was first stated formally by somebody in the 1800s, mid 1800s. You know, why it took somebody so long, it took people so long to state such a simple concept formally, I have no idea. But this guy here, whose name I can't pronounce, is the guy who first stated it formally. Applying the pigeonhole principle in a group of 6 people, must there be at least 2 who were born in the same month? Of course not, because 6 is less than 12. You can have somebody born in January, February, March, April, May, and June, and nobody shares a month. But a group of 13, there must be at least 2 who were born in the same month. How about residents of New York City? Must there be at least 2 people with the same number of hairs on their head? Why anybody would care, I have no idea. But the answer is yes. In this example, the pigeons are the people of New York City, and the pigeonholes are all the possible numbers of hairs on any individual's head. The population of New York City is known to be at least 8 million people. And the maximum number of hairs on any person's head is known to be less than 300,000. So 8 million is greater than 300,000, so there must be at least 2 people that have the same number of hairs on their head. But like I said, common sense, just formalized. Application to decimal expansions of fractions. This is a use for the pigeonhole principle. One important consequence of the pigeonhole principle is the fact that the decimal expansion of any rational number either terminates or it repeats. A terminating decimal is one like 3.625, and a repeating decimal is one like 2.38246 with a bar over the 2, 4, and 6. Where the bar over the digits means that these digits are repeated forever. Let a and b be integers and consider a fraction a divided by b, where for simplicity a and b are both assumed to be positive. The decimal expansion of a over b is obtained by dividing a by b, as illustrated here for 3 divided by 14. And I go through the long division of it all. And let R0 be a, and let R1, 2, and 3 be the successive remainders obtained in the long division of A divided by B. By the quotient remainder theorem, each remainder must be between 0 and B minus 1. In this example, A is 3 and B is 14, and so the remainders must be between 0 and 13. If some remainder Ri equals 0, then the division terminates, and A over B has a terminating decimal expansion. If no R sub I equals 0, then the division process and hence the sequence of remainders continues forever. By the pigeonhole principle, since there are more remainders than values that the remainders can take, some remainder value must repeat. Rj equals Rk for some indices j and k, with j being less than k. This is illustrated below for A divided by A equals 3 divided by B equals 14. So it follows that the decimal digits obtained from the divisions between Rj and R sub k minus 1 repeat forever. In the case of 3 divided by 14, the repetition begins with R7 equals 2 equals Ri, and the decimal expansion repeats the quotients obtained from the divisions from R1 through R6 forever. So 3 divided by 14 is equal to 0.2142857 with a bar over the 142857. The generalized pigeonhole principle. A generalization of the pigeonhole principle states that if n pigeons fly into m pigeonholes and for some positive integer k, km is less than n, then at least one pigeonhole contains k plus 1 or more pigeons. This is illustrated in figure 942. M equals 4, n equals 9. K equals 2 because 2 times 4 is less than 9. At least one pigeonhole contains 3 or 2, the k plus 1, 2 plus 1 or more pigeons. Generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y of m elements, and for any positive integer k, if km is less than n, then there is some y, which is an element of big Y, such that y is the image of at least k plus 1 distinct elements of x. So, applying it. Show how the generalized pigeonhole principle implies that in a group of 85 people, at least 4 must have the same last initial. In this example, the pigeons are the 85 people and the pigeonholes are 26 possible last initials of their names. Consider the function L from people to initials defined by the following arrow diagram. Since 3 times 26 is 78, which is the largest multiple of 26 less than 85, the generalized pigeonhole principle states that some initial must be the image of at least 4 people, k being 3 plus 1 is 4. Thus, at least 4 people have the same last initial. Consider the following contrapositive form of the generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if for each y that's an element of y, the inverse function, the inverse of f of y has at most k elements, then x has at most km elements. In other words, n is less than or equal to km. I don't know if that's entirely clear. Maybe I should read that one over again. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if for each element little y is an element of big Y, the inverse of f of little y has at most k elements. Then x has at most km elements. In other words, n is less than or equal to km. Okay. All right. Expound on that? Well, if for each y that's an element of big Y, of the set y, the inverse of the function has at most k elements. Then x has at most km elements. In other words, n is less than or equal to km. So if the inverse function has a certain number of elements, maximum in each for each value of y, of little y, then x can have k times m elements. X has at most km elements. So you do the k times the number of elements in y, and you get a greater than or equal to number of the elements in set x. I'm sorry? Oh, okay. Basically, if the set x has less than or equal to the maximum number of elements going to each element of x times the number of elements coming from y. Let me see if I can put this on in a diagram here. So you have y, okay, and you have so many elements, okay. X has n elements. Oh, it's not. It's not positive. It's say here you have. Let's give a. So you have 8 elements here, and let's say 9 elements here. Okay. So here you have a function illustrating the pigeonhole principle. You have an element with 2 values of x mapping to y. Okay. So, and this is n number of elements. The maximum number of k, which is the number of the inverse function. So y, the inverse of y would be 1 here, 1 here, and then here would be 2. So k would be 2.
Okay, the amount
going back from y to x. Yes. So km is greater than or equal to n. In this case, k is 2, and this is 8 and 8. I'm sorry? It's the maximum number of mappings from y to x. Yeah. And this 2 times 8, k is 2, because that's the maximum number of k. M is 8, the number of elements, and this is 9. So it holds true that n is less than or equal to the maximum number of. So, yeah. Does that make sense now? Yeah, it's so it's yeah, in the pigeonhole example, you have 8 pigeonholes, 9 pigeons, right?
So what would you title this relation? So like, would you call both n and m pigeonholes, or
no? N is the number of pigeons. So basically, you take the pigeonholes and take the maximum number of pigeons in a hole, in this case 2, multiply it by the number of holes you have, which is 16 in this situation. That's going to be greater than or equal to the number of pigeons that you have. Make sense? Okay. You can go back to.
Will that setup always hold true for different pigeonhole examples, or no?
Yeah, it will hold up in all pigeonhole examples. So, yeah. And proof of the pigeonhole principle, as if you need to prove common sense. The truth of the pigeonhole principle depends essentially on the sets involved being finite. We know that a set is called finite if and only if it is the empty set or there is a one-to-one correspondence from one from 1, 2, 3 to n to it, where n is a positive integer. In the first case, the number of elements in the set is said to be 0. In the second case, it is said to be n. A set that is not finite is called infinite. Thus, any finite set is either empty or can be written in the form x1, x2, etc. to xn, where n is a positive integer. So for any function f from a finite set x with n elements to a finite set y with m elements, if n is greater than m, then f is not one-to-one. It's not a one-to-one relation between x and y. Okay? And an important theorem that follows from the pigeonhole principle states that a function from one finite set to another finite set of the same size is one-to-one if and only if it is onto, which I believe is a term you'll learn in in chapter 6 if you do the extra credit homework. That x and y be finite sets with the same number of elements, and suppose f is a function from from x to y, then f is one-to-one if and only if f is onto. Basically, onto means, if I'm recalling correctly, each element of x is if f, the function f, corresponds to a distinct value in a distinct element in y with no duplications. I believe that's. They both have n elements. They have the same number of elements.
No, I'm not talking about y. I'm talking about onto. It's onto referring to hidden in a set. You're doing a number, then another number, then onto. Well, the ellipses and it's in and onto the same.
No. Onto is just a characteristic of the relationship between the sets. Yeah. And that's it for this deck. We'll go to section 5. Counting subsets of a set. Count combinations. The number of subsets of a size R that can be chosen from S equals the number of subsets of size R that set S has. Each individual subset of size R is called an R combination of the set. Let n and R be non-negative numbers, with R being less than or equal to n. An R combination of a set of n elements is a subset of R of the n elements. So it's just different combinations of elements in the set make up the subsets. The symbol n choose R denotes the number of subsets of size R, or R combinations, that can be performed from a set of n elements. And we went through how to calculate that number earlier in the semester. Consider a set of consisting of 4 people: Ann, Bob, Sid, and Dan. Given the set, each subset of size 3 has a 3 combination of its elements. And how many ways can the people in the set form a committee of size 3? Let's see here. Each combination is given here. Thus, the 4 choose 3 is equal to 4. Number of ways the people can in the set can form a committee of size 3 is the number of distinct such committees, which is the same as the number of subsets of size 3, and equals the number of 3 combinations of elements in the set. There are 4 ways that can be done. There are 2 distinct methods that can be used to select R objects from a set of n elements. In an ordered selection, it is only what elements are chosen, or is not only what elements are chosen, but also the order in which they are chosen that matters. 2 ordered selections are said to be the same if the elements chosen are the same, and also if the elements are chosen in the same order. An ordered selection of R elements from a set of n elements is called a R permutation of the set. In an unordered selection, on the other hand, it is only the identity of the chosen elements that matters. 2 unordered selections are said to be the same if they consist of the same elements, regardless of the order in which the elements are chosen. An unordered selection of R elements from a set of n elements is the same as the subset of size R or an R combination of the set. How many unordered selections of 2 elements can be made from the set 0, 1, 2, and 3? An unordered selection of two elements is the same as a 2 combination or a subset of size 2 taken from the set. You can list these systematically as here. Since this listing exhausts all possibilities, there are 6 subsets. Thus, 4 choose 2 equals 6, which is the number of unordered selections of 2 elements from a set of 4. When the values of n and r are small, it is reasonable to calculate values of n choose r using the method of complete enumeration. But when n and r are large, it is not feasible to compute these numbers by listing and counting all possibilities. The general values of n choose r can be found by a somewhat indirect but simple method. An equation is derived that contains n sub choose r as a factor. When this equation is solved to obtain a formula for, then this equation is solved to obtain a formula for n choose r. Write all 2 permutations of the set 1, 2, 3. I'm not going to go through all that. And solve the equation for 4 choose 2. According to theorem 923, the number of 2 permutations of the set is 4 factorial divided by 4 minus 2 factorial. Cancel things out, you get 12. 4 times 3 is 12. If n and r are integers and r is greater than or equal to 1 but less than or equal to n, then the number of r permutations of a set of n elements is given by the formula shown here, or equivalently, the n factorial over n minus r factorial. Now the act of constructing a 2 permutation can be thought of as a 2-step process. Choose a subset of 2 elements from the set. Choose an ordering for the 2 element subset. You can see here how it works out. You choose the two combinations, and then you write the two orders in which they can be for each combination, and you get a total of 12. Number of ways to perform step 1 is 4 choose 2, the same as the number of subsets of size 2 that can be chosen from 1, 2, 3, 4. The number of ways to perform step 2 is 2 factorial. The number of ways the elements in a subset of size 2, because the number of ways of performing the whole process is the number of 2 permutations of the set, which equals 4 permutations of 4, 2. It follows from the product that rule that the permutations of 4 and 2 equals 4 choose 2 times 2 factorial. Solving the equation for 4 choose 2 equals this here, and then we know that P of 4 and 2 is 4 factorial divided by 4 minus 2 factorial. So substituting yields this here, which is the 4 factorial divided by 2 factorial times 4 minus 2 factorial. Computational formula for n choose R. The number of subsets of size R, or R combinations, that can be chosen from a set of n elements is given by the formula n factorial over R factorial times n minus R factorial, where n and R are non-negative integers, with R being less than or equal to n. Seems like we went through that equation earlier in the semester. This one right here? Yeah. Consider again the problem of choosing 5 members of a group of 12 to work as a team on a special project. How many distinct 5-person teams can be chosen? The number of distinct 5-person teams is the same as the number of subsets of size 5 that can be chosen from a set of 12. This number is 12 choose 5. Multiply it out, expand it, do a lot of canceling. You end up with 11 times 9 times 8, which is 792. So use the multiplication rule to show that k of m and n, or sub m and n, is complete bipartite graph on m and n vertices, and has a complete bipartite graph on m and n vertices has mn edges. Now let's look at that. A complete bipartite graph on m and n vertices, k of sub mn, is a simple graph whose vertices can be divided into 2 distinct non-overlapping sets, say V with m vertices and W with n vertices, in such a way that there is exactly one edge from each vertex of V to each vertex of W. There is no edge from any one vertex of V to any other vertex of V. And there is no edge from any one vertex of W to any other vertex of W. Label M and N vertices as V, M vertices of V as V1, V2, V3, etc. Think of constructing the edges between the vertices of V and the vertices of W as an M-step process. For each integer k from 1 through m, draw exactly one edge from vk to each of the n edges of w. It should be the n vertices of w. Because each step can be performed in n ways and there are m steps, by the multiplication rule, there are m times n ways to construct all the edges. Thus, k of sub m n has m times n edges. We didn't do that one. The game of poker is played with an ordinary deck of 52 cards. Various 5-card holdings are given special names, and certain holdings beat certain other holdings. The named holdings are listed from highest to lowest: royal flush, straight flush, 4 of a kind, full house, flush, straight, 3 of a kind, 2 pair, 1 pair, and no pairs. So how many 5-card poker hands contain 2 pairs? Well, let's see here. Yeah. Consider forming a hand with 2 pairs as a 4-step process. Choose the 2 denominations for the pairs. Choose 2 cards from the smaller denomination. Choose 2 cards from the larger denomination, and choose 1 card from those remaining. The number of ways to perform this step 1 is 13 choose 2, because there are 13 denominations in all. The number of ways to perform each of steps 2 and 3 is 4 choose 2, because there are 4 cards of each denomination, 1 in each suit. The number of ways to perform step 4 is 44 choose 1, because the 5th card is chosen from the 11 denominations not included in the pair, and there are 4 cards of each denomination. So, of the number of possible combinations, you multiply it all out, is 123,552 ways you can get to pair in a standard 5-card hand of poker. Just a little statistic. I read somewhere a little comparison of odds. You are more likely to die in your next vehicle ride than to get a royal flush playing poker. Yeah, it's insane that it would be that difficult to get a royal flush in poker.
What is it?
10, Jack, Queen, King, Ace of the same suit. So there's 4 possibilities out of the millions of possibilities of.
This is to get that adjacent.
But yeah, the statistics are the probabilities are that you get struck by lightning before you get a royal flush. That sort of thing. It's oddly enough, I have gotten a royal flush playing poker in Vegas, but neither. Nobody wanted to play with me after that. Everybody left the table. They were like, no. Let's see here. We got okay. Consider the various ways of ordering the letters in the word Mississippi. How many distinguishable orderings are there? Now, this isn't so straightforward because there are duplications of letters. There's 4 S's, there's 4 I's, 2 P's. Because copies of the same letter cannot be distinguished from one another, once the positions for a certain letter are known, then all the copies of that letter can go into the positions in any order. It follows that constructing an ordering for the letters can be thought of as a 4-step process. Choose a subset of 4 positions for the S's. Choose a subset of 4 positions for the I's. Choose a subset of positions for the 2 P's. And choose a subset for one position for the M. Since there are 11 positions in all, there are 11 choose 4 subsets of 4 positions for the S's. Since the 4 S's are in place, there are 7 positions that remain empty. So there are 7 choose 4 subsets of 4 positions for the I's. After the I's are in place, there are 3 positions left empty, so there are 3 choose 2 subsets of 2 positions for the P's, and that leaves just 1 position for the M. Hence, by the multiplication rule, it's 11 choose 4 times 7 choose 4 times 3 choose 2 times 1 choose 1, which is 34,650 when you multiply it all out. Permutations with sets of indistinguishable objects. Theorem 952. Suppose a collection consists of n objects which n1 are of type 1 and are indistinguishable from each other. N2 are of type 2 and are indistinguishable from each other, etc. to n sub k are of type k and are indistinguishable from each other. And suppose that n1 plus n2 plus n3, etc. to nk equals a total of n. Then the number of distinguishable permutations of the n objects is given by this equation, n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, etc. to n sub k factorial. Some advice about counting. A group consists of 5 men and 7 women. How many teams of 5 can contain at least 1 man? Imagine this is the incorrect solution, which I don't know why they didn't include the correct solution, but this is the incorrect way of doing it. Imagine constructing the team as a 2-step process. Choose a subset of 1 man from the 5 men. Choose a subset of 4 others from the remaining 11 people. Hence, by the multiplication rule, there are 5 choose 1 times 11 choose 4, or 1,650 5-person teams that contain at least 1 man. Analysis of the incorrect solution. The problem with the solution above is that some teams are counted more than once. Suppose the men are Anwar, Ben, Carlos, Dwayne, and Ed, and the women are these ladies. According to the method described previously, one possible outcome of the 2-step process is as follows. These combinations. And then in this case, the team would be Anwar, Ben, Gail, Inez, and Jill. Outcome of step 1, but another possible outcome is this one, which also gives the same team. Thus, this team is given by 2 different branches of the possibility tree, and so it is counted twice. But they don't go into the correct way to count it. I'm not sure. I didn't spend a whole lot of time thinking about this one. Just frustrated with the incompleteness of the slides. Got in the way. But what time is it getting to be? 2:30? Okay, I think we have time for one more section. I think it's about 24 or 25. Yeah. 6. Let's see here. It is 23. Okay. Are combinations with repetition allowed? In this section, we ask how many ways are there to choose R elements without regard to order from a set of N elements if repetition is allowed. A good way to imagine this is to visualize the N elements as categories of objects from which multiple selections may be made. Definition and notation. An R combination with a repetition allowed or a multiset of size R chosen from a set X of N elements is an unordered selection of elements that is taken from X with repetition allowed. If the set X equals X sub 1, X sub 2, etc. to X sub n, we write the R combination with repetition allowed or a multiset of size R as the list of elements in square brackets. You use curly brackets for the big set. The subset would be in square brackets, where each element X sub I sub j is in X, and some of the X sub I sub j may be equal to each other. Write a complete list to find the number of 3 combinations with repetition allowed or multisets of 3 that can be selected from the set of the numbers 1, 2, 3, and 4. Observe that because the order in which these elements are chosen does not matter, the elements of each selection may be written in increasing order, and writing the elements in increasing order will ensure that no combinations are overlooked. So, combination starting with 1, combination starting with 1 and 2, 1 and 3. Yeah, it gets kind of tedious here. Thus, there are 23 combinations with repetition allowed. The number of R combinations with repetition allowed, or multisets of size R, that can be selected from a set of N elements is R plus N minus 1, choose R. This equals the number of ways R objects can be selected from N categories of objects with repetition allowed. All right. A person given a party wants to set out 15 assorted cans of soft drinks for his guests. He shops at the store that sells 5 different types of soft drinks. How many different selections of cans of 15 soft drinks can he make? Well, think of the 5 different types of soft drinks as the N categories, and the 15 cans of soft drinks to be chosen as the R objects. So N equals 5 and R equals 15. Each selection of cans of soft drinks is represented by a string of 5 minus 1 vertical bars to separate the categories of soft drinks, and 15 crosses to represent the cans selected. For instance, this string here represents a selection of 3 cans of soft drinks of type 1, 7 of type 2, none of type 3, 3 of type 4, and 2 of type 5. The total number of selections of 15 cans of soft drinks of the 5 types is the number of strings of 19 symbols, 4 of them bars, and 15 of them X. So you do the math out here and you come up with 3,876 ways of arranging the cans. I do skip that one and that one. Oh. Okay. Counting triples. IJK, where I is between 1 and J, which is between I and K, which is between J and N. If N is a positive integer, how many triples of integers from 1 through N can be formed in which the elements of the triple are written in increasing order but are not necessarily distinct? In other words, how many triples of integers I, J, and K are there with that arrangement? Any triple of integers can be represented as a string of n minus 1 vertical bars and 3 crosses, with the position of each of the crosses indicating which 3 integers from 1 to n are included in the triple. The table sheet below illustrates this for n equals 5. Thus, the number of such triples is the same as the number of strings, n minus 1 bars and 3 x's, which is 3 plus n minus 1, choose 3, or n plus 2, choose 3. Do the math out and do some canceling and expanding and all that sort of fun stuff, and you get n times n plus 1 times n plus 2 all over 6. How many solutions are there to the equation x1 plus x2 plus x3 plus x4 equals 10 if the x's are non-negative integers? Think of the number 10 as divided into 10 individual units with the variables x1, x2, x3, and x4 as 4 categories into which these units are placed. The number of units in each category, xi, indicates the value of xi in a solution of the equation. Each solution can then be represented by a string of 3 vertical bars to separate the 4 categories and 10 crosses to represent the 10 individual units. So, for example, in the following table, 2 crosses under x1, 5 crosses under x2, and the 3 crosses under x4 represent the solution 2, 5, 0, and 3. 2 plus 5 plus 0 plus 3 is equal to 10. Therefore, there are as many solutions to the equations as there are strings, often containing crosses. Strings of 10 crosses. Okay, I missed a space in there. Okay, there are strings of 10 crosses and 3 vertical bars, namely 10 plus 3, choose 10. And expand it out, do some cancellation, equals 286. Deciding which formula to use. Earlier we discussed 4 different ways of choosing k elements from n. The order in which the choices are made may or may not matter, and repetition may or may not be allowed. The following table summarizes which formula to use in which situation. I would say write this table down or print it out from the slides from Canvas. You might just need it on the final.